Everyone, I want to introduce John Sarracino. He is a postdoc at Cornell, and he's got some history with Galois. He's currently helping out on the Safe Docs project through Cornell there, and he was a summer intern at Galois in 2019. So I guess that's it. Go ahead, John.
Whoa, thanks, Richard. I really appreciate it. Yeah, so this is a talk on some of the work of my postdoc, and the whole idea here is to sort of bridge some of the gap between foundational verification in theorem provers and the automation of auto-interactive verification. So that's the title, but cool. So I guess the motivation here is that interactive theorem provers basically enable you to build certified systems with very powerful guarantees and prove rich properties about them. But the downside here is that there's a substantial proof effort that goes into such systems. So I put Sisyphus up because like you kind of always have to include Sisyphus in the verification burden of real systems in theorem provers. And I guess if Simon happens to be in the audience, he might commiserate a little bit here, but for some context, a verified kernel, cell 4, took about 2.2 person years to implement, and there was a 10x increase in the actual proof effort that it took to prove that the implementation was correct. So it took 20 person years. And this isn't just limited to cell 4, it's just something that's been generally observed about certified systems. The effort of proving the system correct is substantially higher than the effort of actually implementing the system. And I guess zooming out a little bit, the reason this is happening is because in theorem provers and verification, there's sort of a trade-off between the proof effort of the proof engineers and the expressiveness of the system. So on one hand, you have very automated verification systems such as SAW and Liquid Haskell and Spec Sharp. And these require relatively little verification burden. It's still above, a normal programming language, but the verification burden is relatively small because the system is doing quite a bit of work for you in terms of automating the proofs. And then sort of in the middle, there's this category of provers called large kernel provers. So this includes PVS and F-star and stuff like this. And so these are still interactive theorem provers, but they have an SMT solver in the kernel, so they can leverage the automation of SMT solvers. So they're more expressive than the autoactive provers, but they also require a little bit more effort. And at the far end of the spectrum, you have so-called small kernel provers, such as Isabelle, Paralotic, Coq, and Lean. And these are all theorem provers that are very expressive, and they offer the most solid guarantees, but they also require the most proof effort on the end user. So I guess the thesis of this work is it would be great if we could combine sort of the automation of autoactive verification with the actual expressiveness of a small kernel prover and basically retain the benefits of a small kernel prover while getting the automation of the less expressive autoactive efforts. So in this work, we develop a Coq plugin for SMT-powered proof automation. And one application that our tool enables is gradual verification, where you basically can sketch out a proof and solve the subproofs with an SMT solver, and then replace the proof sketches with traditional rock-solid proofs. And basically, our meta theory ensures that the bulk of the translation from Coq to SMT logic is entrusted. So in other words, we prove that this translation is sound. Okay, so I did not assume any knowledge of Coq for this, just knowledge of functional programming. So I guess the first part of this talk is going to be an introduction to Coq. And I would love to hear questions. So if you have any questions, please speak up. Okay, so I guess as a running example for this talk, I'm going to be talking quite a bit about lists. So I wouldn't say this is pulled straight from the standard library, but it's almost pulled from the standard library. So in Coq, lists are not a primitive. In fact, they're written using the primitives of Coq. And one way to encode lists is like so. So at the top of this definition, we have a generic type, A, and then we have an inductive type family for lists. So that has two constructors. It has nil and it has cons. And if you look at the signature for these constructors, nil has the return type of list, and cons has the return type A to list to list. So these correspond to traditional lists in a statically typed language, in a statically typed FP language. And then there's this infix operator. This is just for printing. So you can actually write out cons using this infix double dot. And then we have a couple list operations defined using structural recursion over the structure of the inductive list. So first we're going to start with append. And the idea with append is it's defined on the left element. If the left element is nil, then it just returns the right element. And if the left element is a con cell, then it cons is the next X onto the recursive result of appending the interior of L with the right-hand side R. So I am using equations here, but these correspond to traditional Coq fixed points. And you'll notice that if you kind of squint and close your eyes, they're similar to Coq fixed points in that they require the recursion to be guarded and on structural sub-elements of the input. So you could write these with fixed points if you wished. It turns out it makes it easier to use the tool if you use equations, so that's why these are in equations mode. Okay, any questions so far? Whoa.
Yeah, this is good.
Cool. And then reverse is defined similarly to append. It's again a recursive function over its input. There's nothing tricky going on here. And I guess the last twist on this example is that we have an arithmetic function length, which is taking in a list and producing a number z that corresponds to the length of the list. So this is using one of Coq's numeric primitives is the wrong word. Coq doesn't have numeric primitives. It just has inductive types, but it's using one of the flavors of numeric type families that people use, in particular binary integer z. So that's what's happening here. Okay, cool. So listen, Coq. So now we'll start with an actual proof. So I could have done this with a demo and like an actual live demo, but I was kind of nervous that I would make a mistake. So I took a bunch of screenshots. If you see something that's confusing, please speak up and I'm happy to clarify what's happening in the proof. So for our first baby proof, we're going to prove that append is associative. So if you look at this statement, a benefit of Coq is that you're able to say like relatively rich things, and it's I would say it's a very natural specification compared to trying to state associativity in stuff like liquid Haskell. So here we have for any list X, Y, and Z, basically the nesting is such that if you append X and Y to Z, it's the same as appending X to appending Y and Z. And I guess another twist here that I didn't talk about too much is equality. In Coq, equality has the meaning that from Coq's perspective, you can replace either side of the equality with the other. So it's a very powerful version of equality, and generally you don't have to define it yourself. So it just comes along for free. Yeah. Okay. So this proof is going to go by induction. And the first step is by saying we're going to do induction over the first list. And this is sort of where the art of theorem proving comes in. You have to kind of think of how the operators are implemented so that the inductive cases match up with the logic of the operator. So in this case, append is recursive on its left input. So we're going to do induction over the first argument to app in the inner cell. Whoa. So we do induction. And what happens here is when you call induction, if you use this tactic, you end up with two cases. So there's a base case when x is nil, and there's a cons case where x is an element little a cons onto an inner list x. So we're going to pause here for a second, and we're going to look at these two proofs. And they both kind of have the same structure in that they're introducing some new variables y and z. So we're going to use a semicolon operator. And what semicolon does is it takes the right-hand side tactic and applies it to both of the subcases generated by left-hand side tactic. So you might think that this is pedantic, but this is how interactive theorem proofers work. You have to spell out each logical step very explicitly and very explicitly guide the structure of the proof. So what we're going to do is we're going to apply intros to both of the cases. And so that's what's happened here. So now we have, so basically now we move the parameters y and z into preconditions. Okay, but we still have two cases. So let's focus on the first case. That's what's happening with this bullet point here. If we look at this, append is defined recursively, and we actually do have a definition of append when the first argument is nil. So what we can do is we can simplify the call to append, actually both of these calls to append. And we do this with something, it's called auto rewrite. This is particular to equations, but if you're doing Coq without equations, it looks like simple, SIMPL. So we're going to auto rewrite, and that simplifies the equation. And at this point, we have a syntactic equality. So we look at this equality and say, these are obviously equal because they're syntactically identical. And so now we can apply a tactic for solving that. It's called trivial. There's actually a lot of tactics that will solve these. It's in some sense the easiest case. So we apply trivial, and that closes the first case. So moving on to the second case, we can apply similar reasoning. And now we end up in a situation in which we need to apply the inductive hypothesis. So we can do this with a tactic called eApply. And if we look in the context, we have this inductive hypothesis, IHX. And if you were being very pedantic, you would specialize the inductive hypothesis to the arguments x, y, and z such that you made sure that the equalities line up. Coq is one of the nice things about eApply is that it will do sort of this reasoning for you, so you don't have to think all that hard about it. So here we can just do something called eApply, and that will directly solve the inductive hypothesis in this case. Okay, so now our proof is done. Okay, so let's zoom out a little bit here. I guess one takeaway is that particularly compared to writing proofs in Spec Sharp or Boogie, induction is pretty easy. It's significantly easier than writing manual loop invariants, at least in my experience. I mean, I've done both styles of proofs, and coming up with loop invariants is pretty horrible. Whereas in this case, you just figure out what element should be inducted over, and then you use the tactic, and it's pretty smooth sailing. Another takeaway is that there are many manual rewrites, and there's a lot of manual reasoning. And in particular, you kind of need some problem-specific knowledge about how append reduces. And in fact, I kind of didn't show it, but this F equal also required a little bit of problem-specific knowledge. So you it's difficult to develop these proofs without knowing the implementations of the actual functions. Maybe even arguably, not really doable. So this is kind of the downside of interactive theorem proving and proofs in interactive theorem provers. And so what we're going to do is we're going to combine the powerful induction of stuff like Coq with SMT automation to handle all of the reasoning about rewrites and handle problem-specific knowledge. So that was the intro to Coq, and next I'm going to show off a couple proofs using Mirrorsolve. This might be kind of quick. If folks have questions, please, like I said, stop me. So going back to this associativity proof.
Actually, I'll take the opportunity to jump in with a question. So on this particular proof, my understanding, I haven't done a ton of Coq myself, but my understanding, it was really important to do the induction before you did the intros. Because if you did the intros first, you'd get the wrong inductive hypothesis.
Yep.
And so it looks like you could do either of those, but one of them turns out to be a dead end, and that you don't find until the end when you can't actually apply the inductive hypothesis. So
Yep.
One of the things that you're going to have to address, I presume, is how do you know which order to do various things to avoid ending up in dead ends?
Yeah, totally. So that's a fantastic point, fantastic observation. In fact, that's probably like that's one of the hardest parts of writing proofs in Coq. So sometimes you do get lucky, and even if you do intros first and then induction later, it might work out to be the right thing. Usually that doesn't happen. Usually, like especially with something like this, you need the quantifiers to be in the right format. So I guess one technique you can do is you can write a proof search script that will either try to do induction on a variable or introduce it, and do that for all variables that are in the for all list. Actually, I ran an experiment on this for using a black box, another black box automation technique on some of CompServe's proofs, and somewhat surprisingly, it did not change the actual success rate a whole lot, which was surprising to me because again, my intuition as well was that generally like the difficult part is figuring out the order of induction. So I would say that in the general case, I think that is again counter to intuition, maybe not as much of an issue as you would expect it to be, but yeah, certainly there are particular proofs like this one where you have to be like very, very careful with the order of induction. Yeah, and I guess a caveat, I mean, I'll bring this up later, but a caveat with this work is that it assumes that the proof engineer actually does the right induction and provides the inductive structure. Yeah. Whoa, thanks, John. Appreciate it. Great question. Okay, whoa. So here's a proof using Mirrorsolve for associativity. I guess it's similar to what you might expect coming from liquid Haskell. And I guess an upside of using this technique is that you basically don't have to do any of the intermediate rewrite reasoning. So what's happening here is Mirrorsolve is translating each case to an SMT query and then discharging it to an SMT solver, and basically trusting the result. So you do have to trust an SMT solver, and you do have to take double negation as an axiom for this to be kosher. But you are able to handle relatively simple proofs like this. And it also scales up a little bit better than normal proofs would scale. So here's another proof. This is stating that reverse is a self-inverse. So if you look at the lemma, it's saying that reverse of a list is the same as the original list. And the manual proof requires a significant number of rewrites. You even have to reach into a helper lemma. Whereas with basically the automation assisted proof, you actually don't have to think about any of this reasoning. So in some sense, this is a little bit more robust than the traditional proof script would be. And then again, similarly for length. So this is another proof. This is using a numeric, some numeric reasoning. So here we have the length of the reverse of a list is the same as the length of the original list. And so similarly, we can straightforwardly discharge this.
I have a question about this one. So Appling is a external lemma, right? This isn't some definition.
It's a lemma like any of these. So
So does Mirrorsolve have a like database of previously proven lemmas that it tries to use? Because it looks like that's important to solve this, correct?
yeah, totally. In fact, that's very crucial for making it work. So that's something I'm not really showing here, but basically Coq has this thing called they have this system called hint databases, and hint databases are pretty complicated. They can do a lot of things, but for the purposes of Mirrorsolve, what we can do is we can take in a hint database and use each of these as a hypothesis. So basically, the way you use the tool is once you prove something, you put it into a hint database, and then in the future, Mirrorsolve will pull from that hint database and use it, have it in the context. So in this case, applen has been proven. So applen is in a hint database. So Mirrorsolve can use it on the right-hand side.
Gotcha.
So is the intuition then for Mirrorsolve that if I've broken it down into the inductive things and I've now got the inductive hypothesis, I've now got in some sense a finite size of term that goes down to root things that I could do some sort of static analysis, complete like SAW-like static analysis
on. Interesting. Yeah, I think the intuition is that as long as you don't require like any of the root proofs to do induction. So I'm not entirely sure how to say this precisely, but basically you can have properties that require induction to prove, but you have to prove them separately. So you can have, for example, applen required induction, but it can still be reused later on without actually having to do induction, right? So basically the intuition here is that the tool and the SMT solver won't do any induction for you, but as long as you provide like all the inductive structure and make it visible to the solver, then it can be used to solve proofs in the future. Right.
So in something like SAW, where we do static, we do unfolding of things, and you end up just with static terms. Obviously, there's a challenge with any kind of inductive or recursive thing that you can only go a certain distance down, and then you have to lemma database it's all the bits that would cause the symbolic analysis to potentially go on forever. It just stops at these things, and these things had better be in my database, in which case I'll be able to say something about them, and then I can do SAT solving. Is that fair?
I think you're giving the tool a little bit too much credit. We're actually punting on that to the SMT solver. So so basically we translate inductive types to an SMT inductive. SMT does have theory of inductive types as a primitive. And the search there then depends on what particular solver you use. So Z3 will try to do exhaustive search and then give up after, and then you have to give it a timeout, otherwise it just spins. CVC5 will do, I think, bounded unfolding, and then if it can't find the result after a bounded number of instantiations of quantified hypotheses, it will say unknown and say, okay, this seems to be true because I can't refute it, but I haven't found a proof yet, so I can't tell you conclusively which way to go. Right.
Okay.
So I guess to sum up, we're reducing it to SMT, right?
Yeah. There's a couple more questions. One from Galwa, I think. One from.
What do you have a choice?
Yeah. So I had two questions. The first one is, so if we compare this to like the Adam Chapala style of Coq proofs, where you basically have like some sort of super tactic that's domain specific. Can you like compare and contrast that approach to this one? Because it feels a lot like a super tactic like Adam Chapala's super tactic and eAuto plus a reasonable hint database could make. I imagine that these proofs are for illustrative purposes and that there are differences in the amount of power with Mirrorsolve versus something like that approach. Can you give me a sense of how those two approaches compare?
Yeah, totally. So you can think of, right. So my intuition is with Adam Chapala style, you're basically encoding proof search into this crush tactic. And then, as you said, using a hint database. So in the case of Mirrorsolve, it's reducing to SMT. So it's using an SMT solver to do search instead of the crush tactic. So you would hope that the SMT solver would be a little bit better at instantiating hypotheses, et cetera, than crush. I guess I don't necessarily have a either a quantitative or a qualitative image of what that difference is in practice. So I think that's a fantastic place to look for a future evaluation. And so that's kind of where I'm at with it. But I would say that my impression from the state of the art of black box solvers, so there's this tool called Hammer, which basically has no knowledge whatsoever of the domain specific proof. And in the evaluation for that work, they found that Hammer outperformed crush and hint databases in terms of handling proofs. So I'm not sure if that directly translates to Mirrorsolve, but I would expect that the results would translate. Yeah.
Oh, interesting. I'll check that out. Thank you.
Yeah.
Did you have a second question, or should I go?
Oh, well, yeah, if I could jump in for a moment, I've got a follow up on John's question. I guess sort of a follow up. Mike, it seems to me like what you're doing is you're basically stating the induction hypothesis as a first order axiom to the solver and asking it to find the instantiations for you. And my experience has been that solvers are not really great at finding those instantiations. Do you have any sense of how much this scales? Like how far can you go before the solver just spins forever? And do you have any sense of that?
Yeah, totally. I mean, so my intuition coming from using Boogie a lot is also that, you never want to give quantified hypotheses to a solver. And I was very surprised by the results of this work because it seemed like, at least for inductive hypotheses in the style of Coq proofs, the SMT solvers are actually very good at doing this instantiation. So I have some numbers later, but I expected that to be an issue, and in practice, it has not been an issue at all, which again was kind of contrary to my intuition and my expectations there. Val?
So I think I have two questions, but the main one was you mentioned that the solver is using those lemmas, but it seems that the reason why these lemmas exist in the first place is that someone tried to do the proof and realized they needed the lemmas. Some lemmas are more overall useful, but some of them are really precisely created just for that purpose. So how would the tool fare without these in existence, and how would you go from, like, if it fails without them, it seems like it wouldn't really help with the very first proof of those?
Yeah, I think that's an accurate intuition. So for example, when I developed this file, I started with the statement that reverse equals the list, and I had no intermediate lemmas. So you try that, and the solver says, okay, I don't know, I can't disprove it, but can't solve it. And so then you kind of have to work backward. Yeah, so that you're correct in that it's sensitive to having like the correct inductive lemmas in scope. I think an upside of doing this in an interactive setting as opposed to like in an auto interactive setting is that in the interactive setting, you actually can use, traditional interactive theorem proving techniques to kind of dig through the proof and figure out where you're missing lemmas. Whereas like in auto interactive techniques, like it's much more of a research question of how on earth do you debug a boogie query that isn't going through, right? So yeah.
Yeah, and my other remark is a bit of the same. Is oftentimes you start a proof and realize you need to strengthen the induction hypothesis, and I don't see how this could help at all with that type of problem where your statement is not of the correct shape to begin with.
Yeah, totally. I think the only thing that it would help out in that situation is that it would tell you that it doesn't know how to solve the proof. So that would give you a hint that like your inductive hypothesis isn't strong enough. And another place it might help out is like if you say something that's explicitly false and then try to prove it, it's much more likely that it'll come back with a counterexample and give you a warning, as opposed to like,
Yeah,
trying to use
that's
crushing.
nice, yeah.
Yeah. So I guess these are some of the benefits of using the SMT solver there.
Can I ask you one more question before you continue on? So my understanding is that this is not actually constructing terms of type prop. So does that mean that it doesn't help me with like dependent programming in set, or can it help me there too?
Let's break that down a little bit. So by the first part, do you mean are we actually interpreting these refutations and reconstructing proofs?
Yeah,
Because
so yeah, I imagine that because you're in prop, you don't actually need to produce terms. You don't actually have to construct proof objects. But if you were to do the same thing in set rather than being in prop, you would run into an issue where you don't have terms to do, for example, dependent pattern matching on or something like that. Is that the case, or is Mirrorsolve doing something behind the scenes to like construct? I guess if you have LEM, right, then that's going to be axiomatized, and that doesn't have a computational interpretation. So you're already hosed there.
yeah, there's nothing computational here. This is all axiomatized. Yeah. Now, having said that, there is hope that you could reconstruct the refutations. There's actually a fair bit of related work on that. And I think at the beginning of this project, SMT solvers weren't producing refutations for our queries, but CVC5 is producing refutations at this point. So it's totally plausible that like, you give it 6 months of engineering and you're able to actually interpret the refutations, which would be really nice. But yeah, at the moment we're just trusting the SMT solver, so there's a bunch of axioms all over the place for trusting those results. Yeah.
Sure, and the Coq style, this makes a lot of sense, right? Because the Coq style is, define first order data types and then prove things over them, rather than the Agda style of, So yeah, it makes total sense. Thank you.
Yeah. Yeah. Cool. Any other questions? Cool. Whoa. So I guess I probably, when you asked about Crush versus Mirrorsolve, I probably should have just skipped straight forward to this slide. So I guess as part of the evaluation for this, I've looked at a couple proof repositories that are in the literature. So if we're looking at these, the first one is Verified Functional Algorithms, which is a textbook by Isabelle and others. And in particular, this is the search tree assignment. So I guess you can think of this as in this style, it's basically writing out a bunch of relatively vanilla Galena code and then proving properties about it. And you have this bespoke inductive type that's defining what the search tree is. The second, so that's the VFA search tree. The second group of benchmarks is pulled from CompCert. So they have a bespoke data type for sets of intervals. And again, this data type is a little bit more dependent. So it's interesting because I guess there's this idiom in Coq of basically defining a first order data type that isn't dependent and implementing operations over it, and then packaging it up into a dependent interface that actually like um, has some well-formedness guarantees baked into the dependent type. So it's interesting because, like, I guess if you think about this idiom, your intuition is that, okay, well, as you said, you can't really do computation, so Mirrorsolve is not going to help out for handling any of the dependent obligations. But it does help out with the proof obligations that are in the, I guess, inner core that isn't dependently typed. So that was what we found there. And I guess this third part is a group theory assignment that I found on Arjun Guha's website. I believe it's pulled from Adam Chapala's book on theorem proving. So it's been like around for a while, but basically it says, okay, here's a group, here's a couple axioms of a group, and then it asks you to come up with a bunch of classical proofs about group theory. And for this comparison here, basically we follow the same inductive structure as the original proofs. So again, we didn't have to come up with the inductive reasoning for these, which was handy. And we compared against Hammer, which in my opinion is the state of the art of black box. You could argue that maybe we should throw Crush in there. I think that's totally fair. It means I need to go figure out how to use Crush. And generally we found that, at least with Hammer, for the group theory assignment, I guess an interesting thing about the group theory assignment is it was all in uninterpreted functions. So Hammer is like, the way they work is they reduce the Coq problem into a query in uninterpreted functions and then send that to an SMT solver. So it's actually not surprising. Hammer and Mirrorsolve basically do the same thing for the group theory assignment, and that's because, you know, it's just using uninterpreted functions. Whereas for the intervals in the search tree benchmarks, actually these had inductive data types that were doing bespoke things, and they also used numerics all over the place. And so we found that Hammer basically, it really only handled the easy base cases, whereas Mirrorsolve was able to scale up to handling the recursive cases as well. Whoa. So, and I guess, again, like I said, my personal expectation going into this is that, you know, we'd put together an evaluation like this and Mirrorsolve would have trouble with a lot of the inductive cases because SMT solvers just blow up with quantified hypotheses. But it seems like in practice, they actually do pretty well. And it did not seem to be an issue, which again was kind of surprising to me. I guess the new generation of SMT solvers is more powerful than when I was in grad school. So that's even like 4 years ago. So yeah. Cool. Any questions?
So you're actually using the like theory of arithmetic for integers and like you're mapping the various theories in Coq to the SMT theories, whereas Hammer is just using uninterpreted functions. Is that right?
That's right.
Okay, got it.
Yeah, I mean, and in defense of Hammer, because their translation only like uses uninterpreted functions, they can handle anything without any configuration. Like you just call the script and you don't have to think about it. So that is a really big plus out of Hammer. Yeah. But I mean, of course, the downside here is then they can't use, you know, SMT's knowledge of arithmetic to handle any of their arithmetic obligations, right? So
and by configuration, you just mean mapping SMT theories to types and things like that, or do you mean is there other configuration?
No, that's it. I mean, I guess. Let's see here. I think I have a caveat. Okay, great. So it's a good segue. So here's roughly how the tool works under the hood. We start with the vanilla Coq goal, and then we use certified reflection to translate into a structured intermediate representation. So this intermediate representation is first order logic parameterized by like end user theories. So I guess the nice thing is because of the way we set things up, you basically don't have to worry about whether we treated variables properly, because shallow Coq variables get mapped onto deep variables in the structured AST. And we have a correctness result so that, you know, this translation is sound. I guess another thing here is that we translate the shallow Coq numeric type into, again, a numeric type within the logic. So this is part of where the configuration is. You need to make sure that you instantiate with, make sure that the core logic is instantiated with something that either goes directly to SMT or can be compiled and desugared into something that goes into SMT. So I guess for those familiar with Coq, NAT is Coq's default inductive type. They're piano natural numbers, and you have a bunch of piano arithmetic operations. Those don't translate one-to-one to SMT because they're only the positive numbers. So you have to do a desugaring where you basically put a bunch of constraints on quantified formulas wherever there's a NAT. And you also need to make sure that minus goes to like the right operator, because NAT minus isn't the same as integer subtraction. So like there's a lot of bookkeeping in there, and that's kind of like if you're not careful, you might like sweep all this under the hood. And this is like where you could be a little bit skeptical of large kernel theorem provers, because you basically don't know where the boundary is on certified code versus stuff that's has to be trusted. Whereas with Mirrorsolve, you actually can verify that these desugarings are correct and make sure that you end up in something that's like directly mappable to SMT. So I guess at the end of the day, we take these first order logic terms and then pretty print them into SMT queries. And I should have negated this bottom here, because we negate and then check for unsat and then treat that as a proof of the original. So it's double negation elimination. And you need to do that when you're working with uninterpreted functions. Otherwise, like, yeah, you can get in trouble there. But well, and in terms of things that we've certified in proof sound, it's we have correctness proofs for the reflection from Coq into the core logic, and then translations around within the core logic. So I guess the trusted code base here is the pretty printing, as well as trusting that the SMT solver does the right thing when it has the pretty printed proof. Yeah. Any questions?
I did want to have one actually. I was wondering, is there any hope for relying on the fact that you are targeting a theory that is decidable in terms of not having to rely on double negation? Like in a theoretical world where you could replay the refutation, like could you finally undo that last step and not require double negation? Or are you too far out on a limb?
Yeah, no, I think that's totally plausible. I mean, you don't have to take my word for it. If you're familiar with the SMT Coq project, they're also a tool that does this, but they kind of stick to the guns of not trusting anything. So they only target theory of bit vectors and proofs it in a very specific format. But as a result, they're able to replay the refutations back into like the original goal. So there's like no trusted code base whatsoever. So yeah, it's totally doable. Having said that, I've not done that, and I have not looked very specifically at the proofs put out by CVC5. So, like, don't hold me to that.
Are higher order propositions just not representable at all, or are they can translate them but just have no guarantee on the solver doing anything useful with them?
What do you mean by higher order propositions?
Just propositions that quantify over other propositions.
Yeah, totally. I personally don't think that's within the scope for a tool like this, because we're targeting SMT, but you can imagine doing as much reasoning as you can with the higher order stuff in Coq. and basically trying to get rid of the higher order parts of the reasoning and then discharging the rest to SMT. That seems like it might be doable. Yeah, but I haven't really worked that out. Yeah, because I would imagine like if you're trying to prove an induction principle is sound, it is proof by structural induction, so you might be able to make use of this work. Yeah, I'm not sure. I have to think on that, to be honest. Cool. Okay. And I guess now that I've talked about the good sides of the tool, I should throw some caveats out there. So one thing that I did not show off in comparing proofs is that there's a configuration burden for using the tool. That's rather unfortunate, but at the moment it is less than the proof effort of writing out the original proofs, but it's kind of close. So I would not say that the tool is quite ready for public consumption because, like, again, you have to spend a lot of time configuring the tool. Another big caveat is, like I mentioned previously, the proof engineer needs to figure out the inductive structure of the proofs ahead of time. And also, you need to be able to trust the SMT solver and assume classical logic because we're doing essentially double negation elimination. So there's some caveats there. Having said that, for future work, the first thing that I'm going after is making sure this configuration burden is as low as possible because it's really not it's a matter of engineering. It's not a matter of research. So I'm currently using metaprogramming to basically automate this as much as possible because ideally when you use the tool, it should be completely push button. And obviously it'd be awesome to reconstruct these proofs. I guess I don't have a great sense of how much or how little effort that will take. Could be a lot, could be not very much. And finally, I'd be very interested to automate real world goals. So if you would be interested in bringing Mirrorsolve and the sort of SMT plus Coq automation into your project, please let me know, and I'd love to collaborate. So cool. Yeah. Okay. That is everything I have for y'all today. Thanks so much for taking the time to listen, and thanks so much for your fantastic questions. Yeah. Cool. Are there other questions?
Maybe I have another one. I just don't know how much things blow up when you translate to SMT. Like, are the simple list final formula like really big, or is it reasonable?
Yeah, that's a great question. I think in practice, I've found that the blow up, it sort of depends on how large the inductive type is. So for lists, it's not too bad because there's only 2 constructors. But basically, I guess the intuition here is for each of the, let me see if I can go back to the equations. Here we go. So for each line of these equations, we're going to add in 2 different axioms that explain how the uninterpreted function acts on instances of the inductive type. So if it's something like list where there are only 2 constructors, then each function only has 2 equations. It's not too bad. If it's an inductive type with more constructors, then that tends to blow up a lot. And I think I found that, yeah, I've noticed that for larger inductive types, that could be pretty significant. Rob?
Yeah, so I just, relaying my experience working with SAW, the vast majority of what we end up reasoning about is actually stuff in the theory of bit vectors. And I'm curious, like, have you hooked up the theory of bit vectors via Mirrorsolve? Like, does it have the ability to do that?
Yeah, actually, that's a great question. So this project came out of another effort on verification. So yeah, I guess it started as a compilation target for a project that did analysis of programs that did bit vector manipulation. So I think in terms of what we've implemented, we only needed to use concatenation, literals, and slicing. So we did not use very much of bit vectors, but that's kind of floating around in the innards. And I guess a big plus of being able to use an SMT solver within Coq is that we had basically an analysis with meta theory proved, and it had this nice property where we could take the verification conditions that came out of the analysis and then discharge them to an SMT solver instead of trying to manually discharge them with LTAC or by hand, right?
Yeah, because that process is horrible. I've done enough for that to know.
Totally. We had it in us to do like a proof of a simple program, and it took like 2 weeks, and we said, wow, it'd be easier to write a pretty printer to like make sure that we never had to do that again. Yeah.
All right, if that's it, then thank you, John. We appreciate it.
Cool. Yeah, thanks so much for having me.
Yeah, thanks. That would